So this talk is about the nonlinear wave equation and the hyperboloidal method applied to that. So let me just show you the nonlinear wave equation. Here it is. On the left-hand side, you can see the wave operator here. And on the right-hand side, you see a nonlinear term. So this is essentially the scalar field phi to the pth power. P is a constant greater than 1. And this phi now lives in n space dimensions and 1 time dimension. This mu here is a constant. It's either plus or minus 1. And as you can see, if this mu here is minus 1, then this has the same sign as the time derivative on the left-hand side. So this leads to an amplification. We also call it the focusing nonlinear wave equation in that case. If mu has the opposite sign, it's called the defocusing nonlinear wave equation. So this equation serves as a model for all sorts of nonlinear wave-like equations in various disciplines. And I can see there are many people from GR here. So of course, this equation is also a model for the Einstein equations. In some sense, a simple toy model. The Einstein equations are essentially also a coupled nonlinear system of wave-like equations. There are all sorts of related equations, for instance, the nonlinear Schrödinger equation, Korteweg, Friese equation, Klein-Gordon, Young-Mills, and also wave map equations. This equation has a particularly rich behavior of solutions, and this is because of this interplay between dispersion from the wave operator and from the nonlinear term here, which can be focusing if mu is minus 1. And so it leads to a concentration, which is sort of the opposite effect than the dispersion that you have from the wave operator. So there's some kind of competition between these two effects. In general, if you choose small initial data, these data will scatter, and this means they will eventually approach a solution to the linear wave equation, whereas large initial data will cause blow-up, at least in the focusing case. There are also certain stable soliton solutions in some cases, and these can prevent the solution from scattering. So there's this famous soliton resolution conjecture, which essentially says that at late times, the solution looks like a collection of solitons and radiation. There has been a lot of recent interest from the mathematical community in these nonlinear wave equations, trying to prove global well-posedness, starting with the work of Bourgain in 1999, and then famously this program by Koenig and Merle in the last decade or so. So a few facts about this nonlinear wave equation. One important property is energy criticality. So first of all, there's a rescaling under which this nonlinear wave equation is invariant. So if you rescale both time and space by the same constant lambda, then if you also scale this phi accordingly by this power here, then the equation is invariant under this rescaling. There's also a conserved energy, which I call E here. So this is a conserved quantity, which means the time derivative of this E is equal to 0. And so this is the equation for the energy. And you can see here this a kinetic term, essentially, which is positive definite. And then here you see the term from the nonlinear potential. If mu is equal to +1, so if it's defocusing, then this is also positive. But if mu is -1, so it's a focusing equation, then this energy does not have to be positive definite. Now, then you can ask the question, is this energy invariant under this rescaling written here? And it turns out it's invariant if and only if this p takes on one particular value, which depends on the dimension n in this fashion here. And we call this p here the critical exponent of the nonlinearity. I call it p crit here. So then we call the equation energy critical, and if p is less than p crit, it's subcritical and otherwise supercritical. Okay, so a general fact about wave equation, solving wave equations numerically, is that we, in most of the situations, we have to deal with an infinite spatial domain. So how do we do this? And this is, of course, I guess, one of the main topics of your seminar, which you all are experts in, probably. The simplest approach would be to truncate the spatial domain. So we have an artificial boundary at some large radius capital R. And there you need to impose some boundary conditions so that you have a well-posed initial boundary value problem. And this is a kind of a difficult business because if you have a nonlinear equation, then you don't know what the correct boundary conditions should be. These exact absorbing boundary conditions, as they are called, also transparent or non-reflecting or radiative boundary conditions, they are only known in general for the linear wave equation, but not in the nonlinear case. So if you just impose some naive boundary condition, such as the Dirichlet condition, this will in general cause spurious reflections from this artificial boundary, which you do not want to have, of course. And moreover, of course, you cannot determine the solution beyond this artificial boundary, so for radii greater than this capital R. And this is a general limitation of this method. So what are ways out of this problem? One possibility would be to compactify the radius, so introduce some new radial coordinate, let's say r tilde, which lives in some compact interval, say from 0 to 1. And you can define this r, the original radius, in terms of r tilde in this way, for instance. A here is some constant, which I've taken to be 6 in the plots below. So if you're interested, this corresponds to 3 spatial dimensions and to a mean curvature of these hyperboloidal slices of 0.5. But we'll come to that in a bit. So then I want to look at the characteristics of the wave equations. So they are the same for the nonlinear and for the linear wave equation. They are just the curves t plus or minus r equals constant. For plus, you have ingoing characteristics, which are shown in red here in the plot. And for minus, you have outgoing characteristics here in blue. Now I plot these characteristics with respect to r tilde, so this compactified coordinate. And then you can see for the outgoing characteristics, they all tend to pile up here towards r tilde equals 1, so at infinity. And this is a problem because for outgoing waves, now this wavelength, as seen with respect to this unphysical r tilde coordinate, decreases towards 0. So eventually the waves fail to be resolved numerically if you have a finite numerical grid. So you will also have to deal with spurious reflections and loss of accuracy as the waves travel outwards. So this is not a good solution. Then what you can do is so-called hyperboloidal compactification. So we introduce a new time coordinate as well. Let's call it t tilde. And this, as you can see here, is basically the equation for a hyperboloid. This a is the same constant as before. Now, if you plot the characteristics with respect to r tilde and t tilde now, you can see the outgoing characteristics just smoothly leave this domain here at infinity, r tilde equals to 1. So there's no problem here with this infinite blue shift. And also there are no incoming characteristics at r tilde equals 1. So this means we don't need any boundary conditions at r tilde equals 1, which we call a future null infinity, because this is the place where the outgoing null geodesics end up. And we can now read off the radiation at infinity at this place here, r tilde equals 1. All right, so here I've also got a plot of some hyperboloidal slices. Here I've plotted them in the original RT coordinates. So here you can see that they're really hyperboloids, so they're everywhere space-like, but they become asymptotically characteristic as r goes to infinity. Also, I've plotted here a numerical grid, which is taken to be uniform in r tilde, which is what I will be doing. So when I solve this equation numerically, I choose a uniform grid in r tilde, but now if I plot it in the RT plane, you can see that these grid points here cluster towards r equals 0. Okay, So much for this little introduction to the hyperboloidal method, which I'm sure you're all familiar with. I want to say a bit about coordinate systems. So I choose polar coordinates. The radius r, and then also some angular coordinates on the sphere. I choose n spatial dimensions, so I have a total of n minus 2 theta angles. So they are basically the elevation angles on the sphere. And then I have the azimuth angle, that is phi, which goes from 0 to 2 pi, whereas these thetas go from 0 to pi. Now, most previous numerical work has actually assumed radial symmetry or spherical symmetry. And there are countless numerical works. Of course, maybe one of the earliest is this paper by Strauss and Vasquez from 1978, which is actually about the nonlinear Klein-Gordon equation, but it's quite similar. There are a few exceptions. For instance, Anil here has evolved the cubic nonlinear wave equations in 3 dimensions without any symmetries. But I'm not aware of anyone having evolved this equation in greater than 3 spatial dimensions. So also in this talk I will not assume any symmetries for the case n equals 3. But if n is greater than 3, I need to do something, right? Because if you take some very large dimension, of course, it becomes computationally completely infeasible if I don't impose any symmetry conditions. But I still want to go beyond the radial case, so I decided to have just one effective angular coordinate on the sphere. Let's call it theta. So this means I impose an SON-1 symmetry. So one effective angular coordinate is left. So let me denote by Sn-1, the n-1 dimensional sphere, unit sphere. Then we have the metric on that sphere, the standard round metric is sigma. And I call delta, with this over circle here, the Laplace-Beltrami operator on Sn-1. Now, if I impose this SON-1 symmetry, then this Laplace-Beltrami operator looks just like this. So you can see it only has theta derivatives, yeah, because it doesn't depend on all the other angles anymore. So this is the only, they are the only terms which are left. Yeah, in 3 dimensions, you just have here plus 1 times cotangent of theta times the partial derivative with respect to theta. And in n dimensions, you correspondingly have a different number here. Okay. So that's basically my little introduction. Now I want to go into a little bit more detail concerning the formulation of the equation that I use. I basically start off with the n plus 1 dimensional Minkowski metric. So n space dimensions and 1 time dimension. Here t is time, then we have the radius, and we have the n minus 1 dimensional unit sphere here. So this is the Minkowski metric, which I call eta. We introduced the new time coordinate just as before in the introduction. Let's call it t tilde. And this a, this constant a here, really is n divided by c. Yeah? So n is the spatial dimension, and the c here is the constant mean curvature of these hyperboloidal slices, essentially. Up to a sine, this is basically a sine convention. So as I said earlier, in the simulations, I'm going to take c is equal to 0.5. Then we also have our compactified radius. This is again just the same formula as I had in the introduction. And now, if you write down the Minkowski metric in these new coordinates, it takes this form. So it basically has the form of a conformal factor, omega times the conformal metric written here. So the conformal factor omega has this form, and as you can see, if r tilde goes to 1, then omega goes to 0. Yeah? So at future null infinity, omega goes to 0. We also have the lapse function and the shift vector here, alpha and beta, which are completely regular functions on the entire domain. Now, if you look at this conformal metric here, you observe that it's actually conformally flat in the spatial part. Yeah? So the spatial metric just has this form. It's dr tilde squared plus r tilde squared times sigma. Yeah, so it's flat. The spatial conformal metric is actually flat. And this is thanks to this special choice of this r tilde. Yeah, so if you choose r tilde in this way, then this comes out to be in this form. So of course, because we have the Minkowski metric, the Ricci scalar of the Minkowski metric is 0. It's a flat metric. But the Ricci scalar of the conformal metric, of course, is not flat. It's not 0. And if you work it out, it comes out to be this expression. And you can either do it basically brute force by computer algebra, or you can use some Gauss-Kodazzi equations. So now we've basically worked out the metric, the conformal metric. Let's turn now to the nonlinear wave equation. Here it is again in our standard coordinates. Now it turns out I also want to define a rescaled scalar field, which I'm going to call phi tilde. It is rescaled by the conformal factor in this way here. Because if you do this, then there is a remarkable conformal identity, which is written here, which says that this combination here, so the wave operator minus this term times the Ricci scalar times phi, is essentially conformally invariant. So it just throws out this factor of omega here to this power. So otherwise this expression here is invariant. So this is very nice because now you can start with this left-hand side expression here. And then on the right-hand side, for the wave operator on phi, I just plug in the right-hand side of my nonlinear wave equation. And for r, the Ricci scalar, I know it's 0. So this just goes away. And then all you have to do is basically combine these powers of omega, and just it turns out to be this term here. Yeah, so you combine this power with this power here from the right-hand side, and you get this power of omega. So this is essentially the nonlinear wave equation written in this conformal language, which I will be solving. Now, to do this numerically, it's useful to perform 3 plus 1, so space plus time decomposition. To do this, I define the unit future directed normal to the tilde equals constant slices. Let's call it nu tilde. This has a Lie derivative, which I have written down here for the scalar phi tilde in terms of the lapse and the shift. Also, we are going to need the conformal mean curvature of the t tilde equals constant slices. So the conformal mean curvature, meaning in this conformal space, k tilde, this is this expression here. And then if you perform this 3 plus 1 decomposition, you can write the nonlinear wave equation in this way here. So you see essentially a second Lie derivative along the normal lines, which is essentially a second time derivative, and then here the Laplacian. Okay, so I want to go to one step further. I also want to reduce this equation by one order in time. So I introduce a new variable, which I call pi tilde, which is just the Lie derivative of phi tilde along this nu tilde. So this means I get an equation for the time derivative of phi tilde, which looks like this. So the time derivative of phi tilde is essentially pi tilde. And then the time derivative of pi tilde is essentially, well, the Laplacian of phi tilde, up to some extra terms. And then you can also see here this nonlinear term from the nonlinearity in the wave equation. Okay, so this is quite a nice equation because it's completely regular at square plus, provided that this exponent here of omega is non-negative. If it's negative, then you have a problem because, as I said, at square plus, omega goes to 0, and then this would blow up. But as long as it's greater than or equal to 0, then there's no problem. And the critical value for which this is the case is when p assumes this value here, n plus 3 divided by n minus 1. I call it p conformal. And it turns out, fortunately, that this is actually greater than p critical. So this means that I can, using this formalism, both evolve subcritical and supercritical nonlinear wave equations. which is important because the qualitative behavior of solutions can be different for the subcritical and the supercritical case. So this critical value here basically is lower than the critical value. Sorry, is greater than the critical value of where you have the invariance, the energy criticality of the equation. So this allows me to actually consider both cases. Okay. By the way, if there are any questions, please feel free to interrupt me. Of course, at the end, we can also have a discussion, but if there are any urgent questions, please just ask. So as far as the formulation is concerned, this is it, basically. We have the equation that we want to solve. I want to tell you a little bit about the energy balance because this is a little bit different on these hyperboloidal slices. I told you earlier that there is a conserved energy for this equation, but this conserved energy is written in terms of the standard slices of Minkowski space, not for hyperboloidal slices. So how can we work out an energy balance for hyperboloidal slices? Well, we start with the energy momentum tensor for the scalar field, which is written here. So this is all in terms of the physical space. Yeah. So this number is the covariant derivative of the Minkowski metric in terms of the physical Minkowski metric. Yeah. Now we have energy momentum conservation, which says that the divergence of this t here vanishes. Then we know there's a killing vector symmetry, which is d by dt. Let's call this killing vector k. And this means now if I contract this energy momentum tensor with k, and then I get a conserved current, which I call E. So this E is divergenceless. And then I can apply Gauss theorem to this divergence-free equation here. And this gives me an energy balance. And this energy balance basically tells me that if I compare the energy computed on two hyperboloidal slices of different hyperboloidal times t tilde, then I get something in between, and this something I can evaluate at infinity, and then this comes out to be a flux, which I call F. More precisely, this is the integrated flux. Yeah? So I take this flux between these two times, t1 tilde and t2 tilde, and I integrate it between these two times along t tilde. And then I end up with this flux, with this energy balance, which has this form. Now I'm going to show you the actual expressions which come out of this analysis, which is a little bit lengthy. So the energy takes this form. And here I've highlighted one term in red, which is actually the potential energy contribution. Yeah? So here you recognize this term from the nonlinear term in the nonlinear wave equation. And the other terms are basically kinetic terms here and terms which come from this conformal compactification and from the hyperboloidal slices. Now, more interesting maybe is the flux. So this quantity on the right-hand side, the integrated flux. So you see it's actually an integral from t1 tilde to t2 tilde along t tilde. And what you can see here is this integral on the n-1 dimensional unit sphere evaluated at r tilde is equal to 1, so at infinity, Fürstenal infinity. And this integrand here is manifestly positive or non-negative, say. And what that tells you is, because we have a minus sign here, that this term on the right-hand side of our energy balance here is actually non-negative and non-positive, sorry. Yeah, so this means that the energy can only decrease. And this is what happens on these hyperboloidal slices. So as the waves travel outwards, you lose energy. You lose energy through future null infinity. This is very different from standard slices in Minkowski space, which end up at space-like infinity, where then you have a conserved energy, but not here. So this equation here is quite similar what in relativity we know as the Bondi mass loss formula. So basically we have equation for the Bondi mass, and on the right hand side you basically have the News function in this flux integral.
Just a
Okay,
quick question. So, sorry,
yeah.
by your definitions of pi and phi, I assume that what's in the parenthesis here is essentially the time derivative of phi, the pure time derivative of. Is that correct? Evaluated at infinity.
You mean this one here?
The spatial derivative of phi minus pi would be the time derivative of phi. So this will be phi t squared. Right?
Okay.
I think that's what comes out for this.
Yeah, that's actually interesting. I think you're probably right, because if you look at I mean, if you look at this equation, the evolution equation for this phi, then yes, because you know the shift and the labs take on special values at future infinity, right? This is what you mean.
Yes,
So
shift is -1, so alpha is 1, and I think this is then ut squared. Sorry, phi t squared. I call it.
Okay.
Yeah. Okay. Thank you.
Yeah, I think you're probably right. This is actually a lot simpler. Yes. Right.
Well, just something quick as well, but I'm sure you'll complete. You said that for supercritical values, the solution blows up. So it's kind of, I don't know, I just want to get intuition about the conserved energy. Like, in a sense, is it such a way that the solution can blow up at the integrated energy at some time slice keeps constant or something like that?
Okay, so I'm not quite sure I understand this question. So you talk about subcritical versus supercritical, right?
The one that blows up, I think, is supercritical, or yes.
The one that blows up.
Or probably I didn't understand correctly. No. Or maybe I forgot the name. It was about the sign of the mu, wasn't it?
They both blow up.
Yeah. So yeah, let me show you the equation again. Yeah. So if this mu is equal to -1, then you have this focusing equation, and then typically for large initial data you have blow up. Yes.
Yes. Sorry, I forgot the names. But yeah, but you have the conserved energy, right? So in a sense, the solution blows up, but the integrated energy at some time remains constant. You know, as the solution grows or something like that.
Yeah, that's correct. Yes.
Okay.
So remember, in the focusing case, this mu is -1, right? So this has the opposite sign. So I mean, this grows, but this also grows. So yeah, so it's no contradiction that this E.
No, yeah, of course. Okay, yeah, that's what I want to do. Thanks.
Okay. All right. Yes. So this is all I wanted to say about this energy balance. And now I want to come to the actual numerical methods which I'm using. So for the radial discretization, well, first of all, in all dimensions, basically, I use equidistant grids. Yeah, so I introduce these radial grid points, which look like that. What you can see here is that these grid points are staggered about the origin, so there's no grid point at r tilde equals 0, which makes life easier because then you don't need to worry about this 1 over r tilde terms, which you do have in the equations. But the outermost radial grid point is actually at future null infinity, so at r tilde is equal to 1. Similarly, for the theta angle, we have also a staggered grid about the axis, so there are no grid points at theta equals 0 or pi, which would be the axis of symmetry, and the polar axis. So again, because you have these 1 over sine theta terms in the equation, they are difficult to evaluate. If you displace the points away from that, it's a lot easier. For phi, there's no such problem, so here I just take grid points which include phi equals 0 and phi equals 2 pi. Now, for the radial discretization, I use centered fourth-order finite differences, which is fairly standard. near the outer boundary, r tilde equals 1, I use one-sided finite differences, which is appropriate because we know that all the characteristics point outwards at the outer boundary. So we can use one-sided finite differences there. And near the origin, I use ghost points. And these ghost points, they basically sit at negative values of the radius. And these negative values of the radius I can fill according to this condition. And this is actually a condition which any smooth function u must satisfy. Yeah, so if you go from r tilde to minus r tilde, then this corresponds to changing theta to pi minus theta and phi to pi plus phi. So if I want to know what is the value at this minus r tilde, I just need to read off this for this positive value of r tilde and at these angles. So then I have ghost points at negative values of r tilde, and then I can just use the standard centered fourth order finite differences, including points which are very close to the origin. Okay, so for the angular coordinates, I use something different. There I use a pseudo-spectral method. And I use a Fourier expansion, so any function on the sphere, I leave out the radial coordinate now for simplicity. Any function u of theta and phi on the two-dimensional sphere, I can expand in this fashion here. So I have basically two parts of this expansion. Here I have cosine functions of L theta, and here sine of L theta. And then for the remaining terms, I have e to the im phi here, in this case only for the even m's, and here only for the odd values of m. So this may look a bit complicated, but this is because any smooth function of the sphere actually must obey these symmetry conditions. So if you look at minus theta, then this corresponds to changing phi to pi plus phi, and if you add theta to theta, if you add pi to theta, then this corresponds to these values here. And you can check that this expansion is precisely the expansion which is consistent with these symmetry conditions. Okay, so in this pseudo-spectral method, I need to be able to transform between the expansion coefficients, ALM here, and the grid point values, u, j, k, which are just the values of u at these grid points, theta, j, and phi k. And because this is a Fourier expansion, there are fast Fourier transform techniques which allow me to transform between these ALM here in the expansion coefficients, and the point values, u, j, k. So the main object in the code is actually the array of point values of these unknowns, which are phi tilde and pi tilde, at these grid points. And all the nonlinear terms, especially the nonlinear term in the wave equation, is then evaluated point-wise. So at each grid point, I compute this pth power of my phi tilde here. And then if I need to, I can transform back to the expansion coefficients AL. Okay, so that's the idea. It's basically a hybrid method. So it's a finite difference method in radius, but a spectral method, pseudo-spectral method in radius, and in the angular coordinates. Right, so then how do we go about integrating this equation forward in time? I use the framework of the method of lines, which means I first discretize in space. Then I get a large system of ODEs, one for each grid point, which I can then integrate forward in time using a standard Runge-Kutta method. I use the fourth order Runge-Kutta method. If you do this, then unless you do something special, this method will in general not be stable numerically. There will be high frequency noise which can grow without bound. And in order to fight this, there is this Kreis-Oligger dissipation. This is a term which is of fifth order, so it's a higher order than the truncation error of my finite difference method in radius. So basically it doesn't affect the accuracy of the numerical method. And this is added in the radial direction only. And this then basically leads to a stable finite difference method. Now, concerning the spectral method, there's also a problem because there's spectral aliasing, which means that certain high frequencies can be misinterpreted because of nonlinearities as low frequencies. And then there can be growth of these frequencies, leading to instabilities. And this can be remedied using spectral filtering. And the filtering rule, which is most often applied, is called the 2/3 rule. And what this means is that basically the top third of all these ALM coefficients, more precisely with respect to L, yeah, so the top third of all L values are removed at each time step, or more precisely at each sub-step of this fourth order Runge-Kutta method. I just set those coefficients, the top third of these coefficients, to 0. In the case of 3 dimensions and without symmetries, there's another problem, because if you imagine the two-sphere and you have an equidistant grid both in theta and in phi, then you can see that there's a clustering of grid points near the poles of the two-sphere. Yeah? So the phi grid points near the poles of the sphere become very dense. And this is a problem because then this very small distance between those grid points near the poles determines the CFL condition. So this determines the time step that you can take, which is then very small. And so what can we do about this? Something which is, for instance, suggested in the book by Boyd, is that you filter out a proportion of the phi Fourier modes, which depends on theta. Yeah? So the closer you come to the pole, or the poles of the sphere, the more phi Fourier modes you remove. Starting, of course, at the top, at the highest Fourier modes with respect to phi. Okay, so after we do this, the time step is still restricted by the smallest distance between neighboring grid points. And this comes out to be essentially quadratic. So this turns out to be h r tilde times h theta. This is the smallest distance. And then the time step, delta t tilde, is chosen to be some constant, the CFL constant lambda times the smallest distance. And typically I use a constant lambda equal to 0.8. For most of the runs which I'm going to show you, the typical numerical resolution is 4,000 grid points in radius, which I call n r tilde, and the angular resolution is taken to be 12 grid points, which is quite low, but it turns out that at least as far as the results I'm going to show you on tails, if you increase this resolution in the angular coordinates beyond 12, the results won't change noticeably. So this is why I sort of get away with this angular resolution. And of course, this, I mean, if you go beyond radial symmetry, these simulations are very expensive computationally. And so you need to see what you can get away with, especially if you want to do tails, which require a very long runtime. Yeah, there's something here about spatial integration, which I think I'm going to skip. So, I mean, this is needed if you want to look at integrals, for instance, in the energy or the flux. Radial integration, you can just do using some standard method like Simpson's method. And concerning the angular coordinates, you can just integrate the Fourier expansion, and you can just, so this is the result that you get. And this can be generalized also to higher dimensions. So then finally, let's go to the results. So first of all, it's always nice to have some kind of sanity check of the code. And for this, I constructed some linear solutions, some exact solutions to the linear wave equation in various dimensions. So you can work those out also in terms of these hyperboloidal coordinates. And they are based on an expansion of the solution in spherical harmonics by Ln. So here in this plot, I show you the difference between the exact solution and the numerical solution. I take the L2 norm of this arrow here as a function of time, t tilde, And here you can see curves for different numerical resolutions. So I take nr tilde to be 250, 500, and 1000. And the angular resolution is fixed, actually here in this case, because I take the initial data to just contain two modes, Lm equal to 1, 1, and 2 minus 2. You can actually get away with an angular resolution up to L equals 2. So this is enough. Because it's a linear equation, you won't get any higher modes. So it's very inexpensive to do, and so this is the difference. And as you can see, if you increase the radial resolution, then you get approximate fourth order conversions. So if I double the number of radial grid points, this goes down by, well, almost a factor of 16, as you would expect, 2 to the fourth. Right, so this is for the linear wave equation for exact solutions. I will come back to some other convergence properties later. Now, first of all, I want to show you a nonlinear evolution, because this is a numerical talk. I feel I need to have at least one movie to show you. So let me try to find the movie. It's always a bit difficult here to play in this PDF file. I will probably have to use some external player. Okay, so let me make this a little bit smaller. Okay, can you see this movie now?
Yes.
It's
Yes.
you see a still frame, of course, first of all. So these are the initial data. These are the initial data of some nonlinear evolution. I think this is it's written here. So it's n equals 5 dimensions under SO4 symmetry, the focusing case, and cubic nonlinearity. And the initial data contain two modes to make it a little bit more interesting. So with L equals 1 and L equals 2, it's superposition. And now all of this interacts, of course, nonlinearly. And so this is the evolution. Yeah, so you see there's some kind of focusing going on in the initial phase, but then very quickly things disperse. So let me show it again. It's kind of difficult to catch here. Once more. So here the initial data, let me do it a little bit slower. Okay, so here's a little bit of focusing going on and then dispersal. So the colors here are always normalized to the entire range of this phi at any given time. The absolute value of this phi is shown basically by the elevation here in the z direction. So you see this phi here now becomes very small. Even you see some colors, it's actually very small.
Have you tried to run a blow-up simulation with high amplitude?
Yes, I have. Yes, unfortunately, I don't have any movie of that, but yes. So I do have some blow-up simulations also. Yes. And this is for this first paper. I wasn't so interested in this blow-up, so I basically discarded those evolutions. But yes, of course, it would be very interesting to look at blow-up also. Yeah.
If I may follow up on this, just out of curiosity, have you ever observed blow-up not at the origin?
Oh, that's an interesting question. I haven't looked very carefully at this, but I think in all the simulations that I looked at, it always blew up at the origin.
So I mean, we can talk about this after your talk, but
Yes, yes.
if I'm pretty sure that you could create blow-up at scry first, and that's kind of unique of the hyperboloidal foliation in their interaction with semilinear wave equations, because if you use standard t-slicing, you never see blow-up outside of the origin. But with hyperboloidal foliations, you can see blow-up at scry first. That could be interesting follow-up.
Yeah, that's an interesting point. Actually, I remember from one of your papers, I think with Piotr,
Yes, with Piotr.
where you described this. And yeah, so this is very interesting. Okay, let's come back to that. So this was just one example of a nonlinear evolution. We can look at the energy balance, which I showed you earlier. And I want to check if this is actually satisfied numerically. So what I plot here is the numerically evaluated energy, this E as a function of t tilde, which is shown here in blue. So the solid curves correspond to the focusing case, the dashed curves correspond to the defocusing case. And as you can see, as expected, the energy decreases as time goes on. Then we have this integrated flux, which is shown in red, so this increases. And then I have the sum, which is computed numerically. So I just add these two curves, the red ones and then the blue ones. And then I get this green curve here for the two cases. And you see this is nearly constant. So as you would expect, so this is the energy balance, again written here. So it should be constant. It should be exactly the initial energy E of 0. Okay, so now you might ask if, so how well is this actually satisfied and does it converge? Yeah, so in the meantime, I've looked at this. So here's the relative error of this energy balance. So this should be 0, but numerically it's not 0, of course. If you increase the radial resolution, you can see convergence here. And if you increase the angular resolution, you can also see convergence. And also what you can see is that the relative error is already quite small. So it's 10 to the minus 8, basically.
How about if you fix the spatial resolution but increase time resolution?
This is also an interesting question. Yes, so I had some cases where I could see some domination by the time resolution.
Because there are these energy conserving time integrators, right? And the Runge-Kutta is not energy conserving. So maybe some of it leaks in time, I thought.
Yes, that's a good point. I could certainly see some cases where it was dominated by time integration error, but not for the resolutions which I'm showing here, and also not for the resolution for the sort of the production ones later. Yeah.
Thank
you. Some other interesting question you might ask is what is actually the contribution to this energy from the potential energy? Yeah? So I remember I showed you in this term for the energy here, this was the contribution from the potential energy. All the other terms here, these are kinetic terms. So you can now compute the ratio of this term, integrated of course, to the entire energy. And this ratio here is shown in this plot, again for focusing and defocusing evolutions. And what you can see is that initially for this, this percentage is quite large, so it's 10 to the minus 1. But then as the evolution goes on, it becomes almost negligible, so 10 to the minus 9 here by the time that the wave has left the computational domain, more or less. Right, so the main subject of this paper was actually tails. So finally, let me show you some results on tails. To compute tails, I need to extract the field at some fixed finite radius, or I can also do it at future null infinity. I call this extraction radius r tilde x. And at this radius, I want to expand the field in spherical harmonics. So I do an expansion of this type. Actually, I use a real basis of spherical harmonics, which are almost the standard ones, except that I take linear combinations with respect to m and minus m. Yeah? So if you're in the case of 3 dimensions without symmetries, these are complex quantities. The standard spherical harmonics are complex quantities. But if you take certain combinations for m and minus m, you get a real quantity. And I want the real quantities, so then the expansion coefficients here are actually also real. And so what does the term tail mean? This means that each of these modes, phi tilde Lm, decay as a power law. So they go like t tilde to the minus q, which also depends on the mode Lm. And this QLM is the decay rate. And this decay rate can be determined from the local power index. And the local power index is basically a logarithmic time derivative of these modes phi tilde Lm. And if this Q here is a constant in this relation here, if you take this logarithmic time derivative, then this comes out to be precisely this Q. So this flows out this Q here that I want, if this is a constant. So one first observation that I made, which I'm not going to discuss in the following any further, is that for focusing and for defocusing evolution, you get the same exponent. So this is why in the following I don't distinguish between focusing and defocusing evolutions. So I get the same decay rates for those two. Next question you might ask is, in 3 dimensions without symmetries, what is actually the dependence on this M? And it turns out that there is no dependence on M as far as I can tell. If you take initial data containing 2 different modes, so here for Lm equal to 2, 1 and 2, 2, and I superpose them, I do a nonlinear evolution with the power p equals to 5, then this will generate some other modes which are not present in the initial data. So for instance, here you can see an L equals 0, M equals 0. I also get an L equals 2 and M equals 0. So they are generated from the nonlinear interaction. And here you can see the modes in a double logarithmic plot. And as you would expect, they are straight lines. So this means this local power index approaches a constant. And you can see from this plot that you get one decay rate here for L equals 0, which is a black line. And for L equals 2 and all values of M, I get the same decay rate. In this case, I get 4 for L equals 0, and I get 6 for L equals 2 and all values of M. And this kind of motivates why I choose this SON-1 symmetry in the following if I use higher dimensions. Yeah, so there I decided, okay, it's very likely, at least from my observation in 3 dimensions, that there will not be a dependence on the other angular coordinates. So I impose this SON-1 symmetry. And so basically I only have this L index in my expansion. I only have one effective angular coordinate. So then you can also look at some conversions for the actual tails. If you increase radial resolution and the angular resolution, you can observe some convergence here. Here for the angular resolution, I've chosen a reference solution because the differences are so small, you basically won't see anything if you plot it like this. So here I plot differences with respect to a reference resolution for a very high resolution. And you see some conversions here, but what you can also see, if you go from, say, in theta 12 to 16, there's not much of an improvement anymore. And this is the reason why for this particular radial resolution here, I choose always n theta equal to 12. Okay, so what is interesting is that there's a radial dependence of these decay rates at any finite radius, as you can see here, for, say, R extraction equal to 0.5, 0.9, 0.99. These curves approach or appear to approach, as far as you can see from these plots, the same decay rate, which would be 6. I mean, for this evolution, which has an extraction radius quite close to future null infinity already, I would have to evolve for much longer, of course, to see it. But they all seem to approach this constant 6. But at future null infinity, you get a smaller decay rate, which is only 3 in this case. So this is quite typical, of course, has been observed many times for different equations. What I'm interested here is, in particular, what is the dependence on these decay rates on the spherical harmonics? Okay, so I'm showing here the decay rate of this this power index Q2, so for L equals 2. And then I show it for various different spherical harmonics. So for L equals 0, 1, 2, and 3. And what you can see is that there are different decay rates which you get here. So for instance, for L equals 3, you have here 8, and then you have 6, 5, and 4. And this is for a finite extraction radius. If you look at square, then you have something different. So there seems to be some kind of degeneracy here. So these three curves here all combine to this decay rate, which is 3 in this case. Okay, so I've run all sorts of simulations and produced a large table. You can see here the different dimensions, n equals 3 and n equals 5. These are the ones that I focused on in this paper. Here are the different spherical harmonics, L equals 0 to 3. And here I've chosen different powers of the nonlinearity. And in each entry of this table, I show you the decay rate, first of all, at a finite radius, which is this left value, but then also at square, which is this value here to the right-hand side. There are some question marks which are values which are uncertain, because this is still quite challenging numerically, because these fields decay very fast, in particular if the exponent p of the nonlinearity is very large. It's quite difficult to observe this decay. Okay, so if you look at this table here, then there seems to be some kind of pattern, but it's kind of a complicated dependence on L and P. So I sat down and tried to figure out some kind of formula for this. And this is what I came up with. So I claim that the decay at a finite radius, first of all, would be this. So it goes like t to the minus ql. And this ql is this expression here. So you have basically two competing terms, L plus P minus 1 and 2L plus 2, and you have to take the maximum of those two in order to get these values in the table. So you will have noticed here in this conjecture, the way it's phrased, I actually go to standard coordinates in Minkowski space, because I believe that at a finite radius, this conformal rescaling will not change anything to the power, to the decay rate. But at square plus, of course, I need to phrase this in terms of hyperboloidal time. And there the decay would be this here, where now this Q tilde, as I call it, for this decay at square plus, has this dependence here on P and L. Now, this conjecture has not been proved. I think it would be very interesting to try and prove it, but there is a special case where it has actually been proved using perturbative techniques. And this is this paper here by Spack and Ison Kmai from 2009. And there they found a decay for this L equals 0, so radial symmetry, which is t to the minus p plus 1. And this is consistent with my formula here. Okay, so that's it. This is just a summary, which I'm going to skip. But maybe more interestingly, I can mention some points which would be worthwhile looking at. First of all, trying to prove this conjecture, as I mentioned. Then there could be a similar conjecture for higher dimensions, in particular for n equals 5. I've come up with some formula there, but it's still sort of on quite weak grounds, I would say, because I need more data, more values of L and P to put this on a firmer footing. As I said, it's challenging numerically because the decay of this field is very rapid for high exponents P. For these simulations that I showed you, I used long double precision, which is quite easy to do in Python. But I feel that I really need something more than that, quadruple precision or even higher, which is, of course, computationally quite expensive. What are further applications of this code? One of them is certainly blow-up, and in particular, the threshold between blow-up and scattering. And this has been looked at in various papers, but I want to mention in particular these two papers here. I think actually we have authors from both papers here in the audience. So this is for the cubic nonlinear wave equation in 3 dimensions, and then also in 5 and 7 dimensions. And there people looked at the threshold between blow up and dispersal, and in particular the kind of universal attractor solution that they seem to find. And I think this would be very interesting to try and reproduce going beyond radial symmetry. Okay, so this is all I wanted to say. Thank you very much for your attention.
Thank you, Oliver, for this wonderful talk. I'm going to stop the recording.